We are here to present on our topic vector network analyzer. Before going to our topic, let's talk about some basics related to our topic. So, what is a network analyzer? Network analyzer is an instrument that measures the network parameters of the electrical networks. Here, the network parameters are like S parameter, that is scattering parameters. We mainly focus on two scattering parameters, they are reflection and transmission. We also measure, the network analyzer also measures the characteristics of electrical networks like impedance, AC voltage, and also current. So there are mainly two types of network analyzers. They are scalar network analyzer and vector network analyzer. Coming to scalar network analyzer, the scalar network analyzer measures only the magnitude part of the sample. So it is called as scalar network analyzer, and the vector network analyzer, it measures both magnitude and also the phase of incident, reflected and transmitted signals. So as it measures the both the magnitude and also the direction, it is called as the vector network analyzer. And let's talk some fundamentals related to our topic. So, what are dielectric materials? Dielectric materials are the materials which hold electrical charges. So, the properties of these dielectric materials are known as dielectric properties, and these are dielectric constant are also relative permittivity. So, what is permittivity? Permittivity is the ability of a substance to store electrical energy when an external electric field is applied. The relative permittivity is the ratio of the permittivity of the substance to the ratio to the permittivity of vacuum. Some dielectric materials are the dielectric properties of materials are defined using a complex permittivity. Here you can see the formula. There are two parts in this formula, the real part and the imaginary part. The real part is the dielectric constant. It represents the ability of a materials to store the electrical energy when an external electric field is applied. And the imaginary part is called the dielectric loss factor. It represents the electrical energy that is absorbed and which is partially converted into heat. And coming to the impedance, what is impedance? Impedance is the measure of opposition to the electric flow. Impedance is a 2D which is represented in a vector form. It consists of two components, that is resistance and reactance. Resistance is the opposition to the electric flow, and resistance is usually measured for a resistor, and reactance is the opposition to the direction of the electric flow. So reactance is for capacitor or inductors. So generally impedance is defined for an AC current, and for a DC current, as there is no reactance, the impedance and the resistance are same. So this is the basic working principle of a vector network analyzer. We use the power of incident, transmitted and reflected signals, and we determine the S factors, and thus the dielectric properties are found. So this is how the vector network analyzer works. Coming to the block flow diagram, the signal is incident from a signal source in which the some is transmitted and some is reflected. The path of the incident and the reflected signals are same, so they are separated using a signal separator. And here the transmitted. These three signals are then sent to the detector, where the powers of these three signals are detected, and then these three scattering parameters, that is reflected, incident and transmitted signals, are then sent to the processor, which then converted into permittivity using various numerical conversion methods. The final output is a graph between frequency, permittivity and the frequency, with y-axis as permittivity and x-axis as frequency. So the final output is displayed.
Now, the first part coming to the source, similar to that of a chemical equipment where we use a fluorescent lamp or a lithium ion lamp, where we'll be producing, like for example, take an FTIR in there, where we'll be heating an hot wire so that we'll get an infrared wave. Similarly to that of equipment in electrical equipment, we'll be using a source of a signal which is having known frequency, and this is actually generated using oscillator, amplifier, and attenuator. So now, what is the signal? A signal is just a wave with defined characteristics like amplitude and frequency. And now we will be giving a frequency as an input so that that frequency signal is generated. Now this signal.
Satvik, please pause the video.
On.
Sorry for the interruption. Like signal is just a wave with a defined characteristic like amplitude and frequency, and we'll be giving a frequency to the source as an input, and that's a type of signal will be generated. For a source, we'll be giving a DC current as an input, such that this source will be converting DC current into AC current with the required frequency and amplitude. Now, for our system vector network analyzer, we'll be generating a source of radio frequency waves with a range of 9 kilohertz to 300 gigahertz as per the required by the user. Now, this RF signal source is mainly of two types, which is sweep oscillator and synthesized signal generator. The main difference is that sweep oscillator is of older technique, whereas in sweep oscillator we'll be getting phases and phase noises. In synthesized signal generator, there won't be any phase and phase noises, and the signal generated in the output will be of more accurate. And coming to the RF, the basic radio frequency source or the signal generator will be having these main three parts, which is an oscillator and then amplifier and then an attenuator. Now the wave is formed in oscillator, which is DC current is converted into AC current with the required frequency. Here the wave is formed, and we will be amplifying the signal wave, and then we will be reducing the power of the signal wave in the attenuator, and then we will be getting the required signal source. Now coming, what is an oscillator? So oscillator is a major equipment in almost every electronic equipment where the DC current is converted into AC current. This is also known as inverter. In oscillator, due to the arrangement of the resistors, capacitors, and inductors, we'll be generating signals like audio frequency, radio frequency waves. Now, this circuit is designed in such a way that required frequency oscillations are will be generated out. Now, first, how oscillations are being developed. So, for example, we'll be taking a system of only which consists of a capacitor and an inductor. Initially, the capacitor is charged capacitor and the switch is open. So, at the very instant of time when we close the switch, the charges in the capacitor starts to transfer into electrons, because being this is an closed circuit, there will be a potential difference, and the electrons will start to move from this capacitor. Now this capacitor will be discharged, and electrons from the capacitor will come into this inductor. Now due to the flow of electrons, there will be formation of current. Now, while there is a formation of current in the inductor, there will be electrical field lines, and due to electrical flow in the due to electrons flow in inductor, there will be magnetic lines generated across the inductor. After in a certain time, the capacitor will be totally discharged, and there won't be any charge left to transfer into the inductor. So at this point, there will be developing a EMF called an EMF, which EMF is nothing but the potential difference at a zero capacitor charge. So EMF is electromotive force. Now now this inductor is totally charged. Now here comes the Lenz law. This Lenz law states that the direction of the current should be changed in such a way that it has to oppose the creation of that direction. So now, according from working principle of Lenz law, this will come. The electrons will flow backwards, so which will be starting to charge the capacitor again, and this inductor will be losing its magnetic field, and it will be charging capacitor. due to these oscillations. So once capacitor is charged and once inductor is charged, capacitor discharged. So this results in formation of oscillations. Due to this formation of oscillations, we can convert DC into AC. Now oscillations are being formed, but in real life or the real case, the oscillations formed are actually damped oscillations due to the resistances provided by the wires and all. So for reducing these damped oscillations and making it into the required undamped oscillation, we'll be giving a continuous input, which is a DC current, and we'll be attaching wires and we'll be taking this circuit as the load to the wires, so that the AC current generated in this load can be converted from these points. So we'll be giving a continuous DC current, and that DC current will be converted into AC current by the oscillations, and then we can send it to, then we can take it out. Now, as I said, these oscillations, now the frequency is being given by the input, by the user. So these oscillations are being developed such a way that these capacitors and inductors are designed such a way that it can produce the required frequency oscillations. So here there are mainly of two oscillators, like Hartley oscillator and Colpitts oscillator, where we'll be using here in both the oscillators we'll be using a transistor. A transistor is nothing but like a PNP junction, PNP junction types. So where this allows the flow of current in different. So here we can see this if there is an like the required flow, then this PNP junction allows to flow the current downward, or according to the input it can flow upward. So this transistor are used to control the flow of current in such a way that we can get the required frequency. So this actually comes under the circuit design part, and the circuit is designed in such a way that we will be getting the required frequencies. So once the frequencies are generated in the oscillators, now it comes to the amplifier. So what does an amplifier do is that it amplifies the wave according to the requirement. So mainly it amplifies mainly two parameters, which is voltage amplifying and current amplifying. Uh, Current amplifying. Now this signal will have a constant power. So when we are amplifying the voltage, which means that when we are increase or decrease the voltage, the current will increase or decrease according to keep or to remain the power constant. Now amplifier is also the same. Now here we'll here also this the design is of circuit. There is a circuit design so that it can so that the amplifier amplifies the wave signal. Here for an understanding, the basic simple is that take if we want to decrease the current, now we can send this signal across the capacitor. Now capacitor is a discharged capacitor. Now when we send these electrons across the capacitor, capacitor gets charged and stores the electrons, and the flow other flow outside flow of the capacitor will be reduced, which means that the current gets reduced according to the required. So in this way, we'll be achieving the amplifying of the wave signal. For example, here we will be getting, if we get an 10 ampere, getting a 10 ampere wave, and what we required is somewhat 8 ampere. So we'll be sending it through a capacitor so that this capacitor stores some charge and only 8 amperes comes out. In this way, we'll be amplifying the voltage or current. Now here comes the attenuator. After the amplified according to the required voltage or current, now we'll be using an attenuator for reducing the power or strength of the wave. Sometimes the power generated by the oscillator will be more, and this cannot be handled by the equipment. So this has to be reduced as per the standards of that equipment. So for this we'll be using attenuator. Attenuator is a very simple design which just consists of the series arrangement of resistors, such that these resistors will oppose the flow of current and reduce the power. So there are many arrangements like balanced T and balanced pi, and these arrangements helps to reduce the power of the signal, and the final output of these attenuator will be the required wave that which we have given to the input as the frequency. Now once the signal is being generated, with the required frequency, it will be sent into the device under test or sample. So what this will happen is this signal will transmit some and will reflect some. So this the transmitted one can be easily detected, but this incident signal and reflected signal has to be separated, and then the power of those should be detected. For this, we'll be using a directional coupler or an signal separation technique, signal separation, which is a directional coupler.
Hi guys. Direction coupler. As we all know that when the signal is passed through the DUT, then it is traced back in the same path as the incident. So we need to separate an incident and the reflected for the power measurements. So we are implementing direction coupler for this purpose. Direction coupler. Direction coupler is a 4-port electronic device which is used to divide up some portion of input signal which is passing through the input port. As we all know that in this figure there are 4 ports. The first port is named as an input port, and the second port is named as an output port, and the third port is named as a coupled port, and the fourth port is named as an isolated port. In the coupled port and isolated port, in the coupled port we can get some part of the signal which we are going to separate from the initial input signal, and in the isolated port we are not getting any signal from the initial port. Okay, mechanism. Now we are going to see how the direction coupler is going to be designed. For to transmit or to transport any signals in the direction coupler, we need a material or transporting media. For this purpose, here we are using a waveguide. Waveguide is nothing but a metallic tube which is used for transporting signals if the frequency is in the range of megahertz. If the frequency is less than the megahertz in the range of kilohertz, then simply air is used as a transporting media. If it is very high than the megahertz in terms of gigahertz, I mean, if the transporting if the frequency of the signal is in gigahertz, then we need optical fibers for transportation. After that, here in direction coupler design, for the to make direction coupler, we need two waveguides which should be uh, placed on each other, like as you shown in the figure. Because in this figure, two direction couplers are placed on each other, and at the interface, we made two holes to create the path difference between the signals. And the distance between two holes is the lambda by 4, which you can see in this figure. Yeah. And also, when the signal is entered into the port 1, it has multiple ways to travel in the direction coupler. The 5 different pathways have been established, has been shown in the figure. In these 5 pathways, the first pathway is that when the signal is entered into the port 1, it can be traveled from port 1 to port 2, or it can be reached to the port 3 via hole 1 and hole 2, and it can be reached to the port 4 via hole 1 and hole 2. Here, if you observe that the some part of the signal is going to be traveled collected gathered at the port 3, and some part of the signal is gathered at the port 4. The signal which is going to be accumulated at the port 3 has the path difference of lambda by 2, because the signal which is going to be at the port 3 has two major signals, that is red color and blue color. The blue color signal which is entering to via the second hole will have the path difference more than lambda by 2 than the red signal. So this path difference will create the interference between the two signals which are entering into the port 3, and the same signals which are entering into the port 4 have the path difference 0. So their interference going to be created. Next slide, please. Yeah. Here, if you have observed that the path difference between the blue and red signal entering into the port 3 is lambda by 2, and the path difference created in the blue and red signal in the port 4 is 0. As we have studied in the FTIR, if the path difference is an integral multiple of lambda by 2, then there is a destructive interference is happening at the port. And if the path difference is an integral multiple of wavelength, then constructive interference is going to be happen in that port. So from this we can conclude that in port 3 completely destructive interference is going to be happen, and there is no signal is going to be stored and also be splitted in the port 3. In port 4, the path difference is 0, which is an integral multiple of lambda. So constructive interference is going to be happen. So from this port we can able to split or divide some part of the input signal which is going to be inserted from the port 1. Okay. Actually, from this direction from each of the direction coupler, we can able to split only one signal only. But in our case, in our vector network analyzer, we need to determine the power of incident and the reflected. So we need two direction couplers which are is in series. First of all, we will see how the signal is going to be transmitted from the source to the duct with only incident. After then, we will go for the reflected. If you have seen that the signal is generated from the source is going to pass through the direction coupler. This direction coupler has been entered from the input port, and it is going to be traveled, and some part of the input signal is going to be coupled with the coupled port, and it is going to be power measurement. That is the thing. And the remaining part which is going to be entered into the port 2 is going to be directed towards the duct. Yeah, next diagram. No. Now, when these input signal is going to be is incident on the device under test, then the device under test will going to be absorb something, in reflect something, and going to be transmit something. The reflection part, which is going to be reflected by the duct, is again passing through the same path as the incident. So we need another direction coupler, which we have used in the series. When this reflected signal is going come back into the same path, it will not go interfere with the incident, because they both are in opposite direction and their amplitude are different, so they won't be interfere with each other. And also, when it is coming from the duct, the second port of the it acts, the entering part, it will act as an initial port, and the above port which is near to it, it will act as an isolated port, and the port which is opposite to it will act as a coupled port. And from this coupled port, we are going to segregate some part of the reflection signal, and from this we are going to measure the power measurement. Next. Now we have separated the reflected signal and the incident signal. Now we want to go to calculate the power measurements. To calculate the power measurements of an AC signal, it's very complicated, and also its accuracy is very low. So we need to convert an AC signal into DC signal. For that purpose, we are using the rectifier. Rectifier will convert the AC signal into DC signal, and then it measures the previous line, and it measures the power of the signal. As we know that rectifiers are many types. There are full wave rectifiers and half wave rectifiers. Full wave rectifiers will completely turn the entire AC form wave into the single polarity DC pulse. It means that when an AC wave is passing through that full wave rectifier, the both positive and negative part of the AC wave is going to be completely transferred into the DC form. In half wave rectifiers, only the upper part or only the lower part, either of these part only going to be rectified. The remaining part is going to be nullified in the circuit. Now we will see how it is going to be happen. Before going to the working mechanism of the full wave rectifier, we need to understand some basic concepts of forward bias, reverse bias, and the diode. As we all know that diode is made up of two different types of conductors, p-type semiconductor and n-type semiconductor. If p-type semiconductor is connected to the positive terminal of the source, then it is known as a forward bias connection. If the negative terminal of the source is connected to the if the positive terminal of the source is connected to the n-type, then it is known as a reverse bias. In reverse bias, current does not flow, because current flow is opposed due to the depletion layer which is formed at the junction. And in the forward bias, current is flowed, which helps to the proceed. So based on this principle, we are going to rectify the AC signal into the DC signal. Now we will go to see the circuit diagram. As you can see that here, the positive cycle means the current will flow in the clockwise direction. Negative cycle means the current will flow in the anti-clockwise direction. When the positive cycle, when the current is starting to move in the clockwise direction, it will pass through the two of the diodes, and it will get rectified. In this part, positive signal is going to be rectified, and by using the negative cycle, remaining part of the AC current is going to be rectified in anti-clockwise direction. This is a circuit diagram which you can see here. After the rectification of the both positive and negative cycles, here we are implementing a voltmeter and ammeter to calculate its voltage and current in the generated DC signal. Voltmeter works based on the principle that it contains a conductor. It contains an inductor. When the voltage is created across the junction, then an electromotive force is generated in this, which reads the potential across the medium. Next. Now we have covered the signal, how the signal is generated in the source, and how it is going to be, how it is going to be incident on the duct, and how it is going to be reflected, and how to separate the incident and the reflected, and how signal separation is going to be used, and the receiver part. Now processor part will be taken.
Now coming to the processor, after the power is detected in the detector, the processor then generates the transmission scattering parameters, which then converted into permittivity using numerical conversion methods. These scattering parameters, as you are converted into permittivity. As you can see, the final output display the two graphs. One is the epsilon real part graph, and the another is the epsilon imaginary part. This graph is the permittivity to frequency graph. This epsilon real part is the dielectric constant part, and the epsilon imaginary part is the dielectric loss factor. In the olden methods, can you go to the previous slide? In the ancient methods, as the equipment and the techniques are not that sophisticated, the graphs are plotted between the S parameters and the frequency. So we then use the numerical conversion methods to find out the permittivity from the by taking the S parameters from the graph. As in the modern times, the equipment is more sophisticated. We directly obtain the graph between the permittivity and the frequency as the final output. Next slide. So what are S parameters? S parameters are scattering parameters that are we use the scattering parameters to detailedly explain the how energy can propagate through a given sample. So S parameters are helps in comparing the powers of incident reflected in the transmitted signals from the source. You can see in the picture this is a two-port system. So usually for a one-port system, the scattering parameter matrix is the S matrix is a 1 by 1 matrix. For a two-port system, it is a 2 by 2 matrix, and for a three-port system, it is 3 by 3 matrix. So the S matrix depends on the number of ports of a system. So let us consider a two-port system. So a 2 by 2 matrix is generated for a two-port system. Generally, the SAB denotes the S matrix, like element of an S matrix. So SAB is the where the A denotes the output signal, and the B denotes the input signal, and SAB denotes the ratio of the power of the output signal to the input signal, that is power of A to the power of B. The 2 by 2 matrix of a two-port system comprises of generally four elements that they are generally denoted by S11, S12, and S21 and S22. So each element is determined by the position of the element. So here the S11 represents the reflection coefficient and S21 represents the transmission coefficient. Next slide, please. So these parameters are defined like S11, S21 and S12 and S22 parameters are defined, and then they are converted into permittivity using the numerical conversion methods. And for a two-port system, we use the Nicholson-Rosberg conversion process. Here you can see the formulae. Using these formulae, the permittivity is determined. You can see the permeability and permittivity. These are the formulae used to determine the permeability and permittivity.
Now coming to now we have seen how does a vector network analyzer work and what are the basic things involved in that. Now we'll be start understanding this by a case study. So for the general measurement procedure, when we are doing, first a vector network analyzer will be setting up and will be setting up the frequencies that we want to measure. We want to measure the variation of permittivity in that frequency range. So we'll be giving this frequency range as the input, and the next one is the another important step of every analytical equipment, which is the calibration. Now the next which will be doing the calibration step, and then we will be placing a sample, and then we'll start vector network analyzer and it will measure S parameters, and then the processor will be converting S parameters into permittivity using numerical methods depending on the S matrix formed, and then the complex permittivity or permeability will be displayed on the screen. Now coming like this in the case study, what we have chosen was microwave absorbing properties of metal functionalized CNT polymer. Here we'll be using a carbon nanotube nanoparticles. These CNT are doped with functionalized like doped with metal oxides like cobalt oxide or iron oxide with different concentrations, and these nanoparticles, doped nanoparticles, are mixed with polyurethane matrix, which polyurethane solution, type of liquid paint solution, and then we'll be mixing it. This solution, this sample is generally coated on these metal plates or any surface, so that this can absorb the microwave or radio waves present in the environment, so that it can be used in stealth applications. Now for finding out how much does it absorb, like the quantity that it can absorb, we'll be using this experiment vector network analyzer, so that we can know the permittivity. uh, Now, for this experiment, we'll be using a frequency range of 5 to 50 gigahertz, and the dielectric properties, which are the permittivity and permeability. These both are actually generated using the equipment which we have also discussed, which is a vector network analyzer. And after the calculation of permittivity and permeability, we'll be finding the reflection losses, and thus how much, and thus we can calculate how much it is absorbing. So being this as a solution, which is a liquid solution, we cannot use a two-port system directly. So for this, a single port system is used. In single port system, only one S matrix is generated, and that single port, for that single port, we'll be using a probe called open-ended coaxial probe. This open-ended coaxial probe design is such a way that inside there is a solid cylinder, solid cylinder, which is a conductor, and that on top of that there is an insulator, and again the conductor is there on top of that. So this solid cylinder, inside solid cylinder is actually made of a metal, and this insulator is of a Teflon. More recently, borosilicate glass filled stainless steel probes are also being used. And now these incident signals are entered into the solution through the conductor. Now these field lines will be entering into the signal, and some of them will be reflected in the same pathway that they have come. So again, now incident and reflected will be going inside, and these will be separating using a signal separator, which is a directional coupler, and then we'll be measuring the scattering parameters, and then we'll get a permittivity. Now we'll be using this open-ended coaxial probe. So the first thing, next step is the calibration, which is very important step for almost every analytical equipment. Here a calibration is majorly of the three types. For open-ended coaxial probe with vector network analyzer, calibration is generally done on three steps. First one is open calibration. In open calibration, the probe was actually exposed to air. When this probe is exposed to air, the total signal generated or coming out of the probe will just go out, which means that there is no reflection. So like we know that there is no reflection, and zero transmissions are there, but if the equipment will be showing some of the error of the reflecting parameter, which means that there is a some disturbance in the pathway, which makes the signal reflected. So this error has to be reduced. For that one we'll be using calibration, and the next calibration is short calibration. In short calibration we'll be using a shorting block and a metallic strip. And in short calibration what we do is we'll send total incident, and we are keeping the shorting block so that the total incident signal will come up, and which means that 100% like 100% reflection should be achieved and no transmissions are there. If there is no 100% reflection, this means that there is some path, some disturbance in the flow of path. Like if for example, if incident of a power of 10 is a 10 watt is generated at the start, at the source, but at outcome, at the entering of the sample, it is just 9. There is a loss of 1, but the detector detects only 9. So this one has to be this one error has to be taken care in the final when we are doing with sample. And next come the load calibration. This is a normal calibration which is done in almost other equipments. Here we'll be using a deionized water, and this probe is immersed in deionized water, and we'll be knowing the dielectric properties of all the dielectric properties with as a function of frequency and temperature. And so this and the known, or the 100% known, can be compared, and we can find the error. So after calibration, we'll be keeping the sample, the polyurethane sample in that in open-ended coaxial probe. We'll be immersing open-ended probe, and then we'll start varying the frequency. Now S parameters are generated. Here only S11 matrix is formed, and which means that only reflection parameter, we'll be comparing only reflection coefficient here. So for converting, now reflection coefficient is generated. Now after converting, like this reflection coefficient has to be converted into permittivity. For that we will be using a SCL method, which is short circuit line method. This is normally of a new, this method is actually solved using Newton-Raphson numerical method only. Here this S11, like we have there's a function given how S11 is dependent on permittivity and permeability. Using Newton-Raphson method, we'll be taking some initial guess, and then we'll be finding uh, the final permittivity. This final permittivity is in complex form. And now the final result, after this numerical method, the software itself will be converting this S11 into permittivity, just like in FTIR, where we'll be using Fourier transform there. Here after final we'll be getting epsilon real and epsilon imaginary. This epsilon real actually represent how much electrical energy it is stored, and imaginary represent how much heat energy that there is a loss due to conversion of electrical energy into heat energy. So final result, we can show that epsilon real and epsilon imaginary are formed with varying frequencies. Thank you.